5:10. So let's get started on our second lecture of this week of reinforcement learning. Again, I think it's going to be it's a fun and exciting topic, and we will go over both some of the new stuff, but also review some of the old stuff from the previous lecture. So I think this is going to be kind of like you'll be seeing some of this material the second time around. So again, now that if seeing for the second time around, you have like maybe there's some confusion or some questions you want to ask, we can use this time as also to have clarifications in addition to introducing new things. So I think this is probably the fourth time we are seeing this slide, but I think it's always good to start with that. The problem formulation that with reinforcement learning, we are continuing to assume a Markov decision process as our problem definition that consists of states, that consists of a set of actions, and a transition model T that goes from states and actions and gives us a probability distribution over next states. And for each such transition, we also have a reward function R. That's that's our problem definition, and what we'll be looking for are policies pi that map states to actions to take. And usually we'll be looking for optimal policies pi that maximize expected utility or expected reward. With reinforcement learning, unlike with this general MDP formulation, we don't know the transition function or the reward function. So these two quantities, we know they exist, but we don't have access to them. So we must actually act in the world and try out a bunch of actions. And last time we've looked at a whole taxonomy of approaches and ways to kind of like divide up solutions to this reinforcement learning problem. And we've looked over all of these methods. And so just going over them in text so that you have a reminder, we've looked first at passive reinforcement learning, which was basically answering the question of how can I learn goodness of states or values just from some passive experiences that was already given to me by some other policy. Maybe it was a human controlling my agent, maybe it was some random exploration, maybe it was just even my actions in the past. But this is what, in passive reinforcement learning, you're reflecting on your experience in hindsight. Then we've also talked about active reinforcement learning, which needed to do this type of improvement that passive reinforcement learning did. But then it also had this additional opportunity / burden of deciding how to act to actually collect more experience. Within the passive reinforcement learning, we've also looked at two classes of approaches. First, we've looked at model-based reinforcement learning, which basically said, well, what I'm going to do is I'm going to try to learn my MDP, specifically my transition function and my reward function, from these experiences that I'm getting. Then I'm going to learn some model of it. It's like build up a model of the world. And then I'm going to use all of the tools that we've learned from last week for solving offline MDPs to solve this MDP, say using value or policy iteration, and get optimal policies this way. So this was pretty straightforward. Then, as an alternative, because it seems somewhat costly to, like, okay, I build a model of the world just so that I can act in it. Well, maybe we can just learn how to act or learn to evaluate our policies on the fly. So we proposed skip learning this MDP and just try to directly learn the V values or the Q values. Within that, we've also looked at several approaches. We've looked at learning values directly for some fixed policies pi. And towards that, we've discussed one of the methods was direct evaluation and temporal difference learning. For example, direct evaluation, what we've done was execute our policy over several trials and just for each of the states count up what's the future reward coming from that state and just averaging over multiple trials. So sometimes we would also call it Monte Carlo evaluation, again by analogy to the operation in Monte Carlo tree search that we've seen during games. But we've said one issue with this is that, well, we've only learned the value function, and so it didn't actually tell us how to act. We could only evaluate our policies. That's what motivated us to look at Q-learning, which we would be able to use both to act and to also find Q-values of optimal policy, even though our experience might not have been optimal. And we will review this, and so we basically derived a Q-based version of temporal difference learning, which we will go over again and also expand on some of the subtleties of it. So that will be our first topic for today. And the second topic for today, we are also going to expand upon active reinforcement learning, and in particular, some of the challenges that arise there, such as exploration, how do I choose actions to find out more about the world, and how do I balance both exploring and exploiting what I already know. And we'll also be talking about ways to evaluate how good our active reinforcement learning algorithm is. Because, well, just having an optimal policy isn't so great if it took you a lot of pain to get there, if it took you both a very, very long time and a lot of negative rewards to get there. So we will try to formalize this notion of evaluating it by describing the notion of regret, which, again, I think ways to evaluate ourselves in artificial intelligence is always good. So we should always be looking for good evaluation metrics. That's going to be our second topic. And the third and last topic that we'll discuss today is going to be approximate reinforcement learning. And that's going to address the problem which actually many of you pointed out in the previous lectures, like, okay, like what if we're assuming that these are going to be tables, but what if the space is very, very large, or what if it's continuous, so we can't even enumerate all of it? And we finally, well, almost finally, will propose one way to deal with it, which is going to be, we'll look at approximate Q-learning, but there would be also, you'd see that this general idea is adaptable to other algorithms as well. And we will also look at policy search, which will be saying, well, maybe learning Q-values is actually not that important. Maybe we should directly focus on learning policies. So that's the roadmap for today, and we'll have a little bit of also of conclusion to part one of this course, because it's the last lecture. Yes, question? I'm not sharing the slides to Zoom? Oh, that is, thank you so much. I should have checked for that sooner. Okay, is it shared now? Does anybody? I think it is being, okay, final, yes, I see. All right. After 9 minutes. I apologize for that. Okay, so again, roadmap of what we'll be looking for. Oh, any other questions? Another? We would check. Let me check with the other staff. I think I want to make sure that I answer this correctly, but do you mind if I get back to you on that? Okay, thank you. Any other question? Okay. So let's start with looking at Q-learning again. And we've talked about it last time, and the way that we arrived at it was we said, well, if we knew the MDP, we could do something like value iteration, but we've adapted it for Q-value iteration, where we've had this recursive procedure. We trying to estimate this Q function Q at some iteration k plus 1. And we've initialized, we know that we've initialized all our, at 0th iteration, our Q value to just all zeros. Then, the way that we've chosen to update this Q value was to average over all of the future successor states, S prime, that can come from being in state S and taking action A. And we weight them by the transition probability of actually observing the state S prime. And for this state S of A of S prime, for this particular transition occurring, we've used a combination of the instantaneous reward that you've gotten for this transition plus the discounted future reward or discounted value. Ideally, what we would say here, it would be an optimal value for state S prime. But we didn't have this function, but we knew that we could use this function. Basically, we could use the highest value in this function Q of K among all of the actions A prime. So this is what gave us this update. The issue that we pointed out with this update is that we cannot compute it without knowing T or R. So using this function, explicitly evaluating this transition function, T is problematic, and explicitly asking for this reward function for a particular transition is problematic as well. So we could do this in solving offline MDPs, but we cannot do this in reinforcement learning. So what we've done instead was to update a Q function as we go. We act in the environment, and we only receive one sample transition from the environment. So let's say we're in state S, then we took action A. The environment landed us in some new state S prime and gave us a reward R. This is just one piece of information that we've received. How do we incorporate that into our learning? Well, we've considered basically like instead of considering all possible successors like we could in this function, we instead evaluate what would be this quantity, this long-term value, for just one particular successor S prime, which is the S prime that we actually received. It's the data that we have. And this quantity we actually can calculate because, well, this comes from our reward, and we know also S prime, so we could use it here, and we assume that we have a previous estimate of this Q function, which is the object that we're keeping track of, and we're updating on the fly. So we've gotten this sample, and then we incorporate it into our Q function with a running average. So we don't just, say, replace the Q value at state SA with this quantity, because that's too aggressive, so to speak. We wouldn't be doing averaging, and it would oscillate back and forth. So what we're doing is we're blending it with the previous value. We're taking this Q value, we're assigning it to proportionally some previous value that we've had for Q with this sample that we've just calculated. So it's a softer update and a softer way to update the average. Maybe another way to think about it is about these two approaches as of two different ways of computing expectation. So what we're really trying to do here is compute, there's too many things on the slide now. We're trying to compute the expectation of this quantity. So we could compute an expectation, and this is some random variable because we have stochasticity, especially over this successor S prime. So the way we could compute an expectation of a random variable, one way is we could consider all the possible values that this random variable can take on and take a weighted sum, weighted by the probability of observing the state of this variable being, or the value of it being k. And this is analogous, really, to what we were doing in Q-value iteration when we knew these probability functions. But another way of computing the expectation of a random variable is if we could draw samples from the distribution of this random variable. If we could draw samples, we could just take the average of the samples, and that would approximate the expectation of this random variable as well. And this basically corresponds to what we're doing in Q-learning. And this does not require knowing any probability distributions. We're just getting these expectations from samples. We're going to expand, if this was somewhat, it's been a long time since you've seen expectations and different ways of computing it. We're going to go into it quite a bit more in the next part of the course, but this is just maybe a quick analogy to think about the difference between Q-value iteration and Q-learning. Any comments or questions? Yes?
If you originally get the first sample, how are you supposed to know the Q of S prime?
Sorry, the...
For calculating the sample, how are you supposed to know Q of S prime, A prime, and the first iteration?
Yeah, the question is how, if you're calculating the sample value, how are you supposed to know this? And it's similar to Q-value iteration. We initialize our Q values for all the S's and all the A's to some value. So we set it we initialize it to 0, for example, at the start of the algorithm. And then as we're learning, it might be being set to, we're blending it with the old value. So we would just set this to 0, and our previous value of it we would set to 0. So we would only be essentially adding the reward to it. Is this clear? Good question. Yeah. Let me quickly check if there's questions on Zoom. Yep, okay. No questions on Zoom. Cool. So let's take a look at an example, again, to clarify this some more. This is an example of a grid world and the table of Q values for each of the states in this grid. And this is a human just manually controlling an agent, kind of moving it left, north, south, east, west. And so what we see here, the first time around, the person basically moved this. We've hit upon some value. We've landed in the state, and what happened here is that we encountered in this particular state, we encountered actually a reward of 10, and I should say for this example, alpha is going to be 1/2. So we've encountered a reward of 10, which, and there were no successors afterwards, so the value of the sample was just 10. We multiplied it by 1/2. All the Q values were initialized to 0, so we've just set this, we're able to set this Q value of the state to 5. Now, what happens the next time? But all of the other Q values, they still are set at 0, so there's nothing informative about what's good for all the other states. But when we slowly start moving, and the next time around, when we make this transition, we now see the value being incremented for this state and going in action east. We've seen this being incremented. And if we think of this state as S and this state for S as S prime, what happened here is if we calculate the sample, well, we didn't get any reward for making this transition. The reward was 0. But then if we look at the Q values now for the successor state, S prime, well, we see that the Q value, there's only really one action, so there's really only one Q value, it's 5. So we see it here, so now the sample value here was 5. We multiply it by 1/2, and we get 2.5. So we've just propagated this kind of like reward that we got in the final good state backwards to some more states. And if we keep doing this more and more times, we actually see that we keep propagating these values backwards and backwards all the way to the initial state, so that at some point in the initial state, we immediately know, okay, this is the right thing, like the right thing to do is to be moving east, immediately, just right away. But yes, question.
Does a sample always does a sample count as a sequence of action from start to a terminal state? Is that always the case?
The question is, does a sample count as a sequence of actions from starts to states? Sample can be, they need not be successive. And we can assume for our purposes, we assume we just receive some transition, that the only requirement is that S prime does need to be an actual successor that you get from S. But exactly what order they come in is actually, we assume no such, we don't really make any assumptions. Here, they were coming in sequentially. But as we'll see actually in the next slide, the algorithm still works even if they don't come sequentially. Yes, question? So the question is, could we and should we make this quantity alpha smaller over time, because we might have issues with convergence otherwise, because these samples that we get are stochastic. And this is what is typically done. You're right, like we can do it, and it does help us to, it does help convergence. So this is what is often done in practice, is like this alpha is getting decayed, usually over time, through other means of decaying it, to stabilize or to reduce this noise and settle on some stable estimates of Q. The other thing that I wanted to point out with this example actually was, that it seems somewhat wasteful how this algorithm works. Because what we're doing, what we've done is we went here once and we found a good state. So it seems like we've really learned what's good about the world. But all of these values, they're still 0. And so we actually need to repeat this behavior multiple times in order to propagate the information about this reward back to the states. So that doesn't, again, and if it's like, it's fine if it's a simulated environment, but if this was actually like you're driving your robot around or so, you'd have to, just to satisfy your Q-learning algorithm, you'd have to drive your robot like in the same good direction like 10 times. That's not very good. So this is a problem, basically, that we need to be repeating these transitions many times to propagate values. And one of the solutions that typically gets used very frequently in practice to address this is to do Q-learning, or is to use experience replay, where you're collecting the transitions, you're collecting these transitions, and instead of just directly using them to update your Q function, you store them and you put them in some memory buffer. And then you're on your own, kind of like at your own pace, you take something, like you take one of the transitions randomly from the replay buffer and you use that for a Q-learning update. So we would receive some sample transition, S prime, from the environment as before. This is what we get from the environment. And then instead of acting on it, we add this to the replay buffer. So we just store it here. And then we can several times repeat multiple Q updates instead of just once per acting in the environment. We would randomly pick a transition, any one of these from our buffer, and then we do a Q learning update based on this transition from the buffer. So you can think of it as, I'm not always acting, or I don't always update my value function when I act, but I might have some kind of like storing a set of memories, and then in imagination, I'm updating what would things have looked like. But this type of like imagination or imaginary experience replay is not tied to be the same as acting in the environment. And this is, I think, another example of AI and neuroscience coming together, where we actually are observing something like this happening in the brain as well, and that potentially people are still building evidence for it, but people are hypothesizing some link between this type of experience replay and what happens in dreams. But this is still, more research is needed. But it's also like a very practical addition to Q-learning algorithms. So we've seen that Q-learning now converges to optimal policy, even if the behaviors that we're seeing are not optimal, even if they're just randomly moving around. And the other really, really nice thing is that, well, Q-learning also gives us a way to act, because if we have this Q function, and actually should be Q star, if we learned an optimal function Q star, well, we can just pick actions for any state by picking the action that gives us the highest Q star value. So we can do now active reinforcement learning with this method. We have everything we need. But then, of course, there are caveats, like which we're going to talk about, such as exploration, and there are these additional caveats that you do have to make the learning rate small enough, as you've pointed out, but you also cannot decrease it too quickly. So this is something that typically gets tuned by hand, unfortunately, still. And I should say, this is one example of how we could use Q-learning to now automatically select actions. So this brings us to active reinforcement learning. Any questions about what we've seen, about about Q learning so far. I'll check Zoom real quick. I see Bayern already answered. Great. So let's look at active reinforcement learning, and in particular this issue of exploration. So as we've mentioned, we need to actually visit states with high rewards to learn something, to learn that they're good, basically. So we need to act to find, basically to find some promising situations. And it presents a trade-off, because how much do we weigh maybe finding some unexplored yet potentially rewarding opportunity versus doing what we already know to be good in the past? And we've seen this trade-off before as well. When we were talking about Monte Carlo tree search, we saw like UCB exploration heuristic, and flavor of it is going to come up in this lecture very soon as well. But before that, before we try to do something like UCB, there's an even simpler heuristic for exploration, which actually works really, really well. And in fact, it's, unless some researchers are specifically researching exploration, this is what's commonly being used to do good enough exploration strategies. And the strategy is this. Well, at every time step, when you need to act, you basically flip a coin. And with some small percentage, epsilon, you act randomly. You just decide on some random action. And with typically a larger probability, 1 minus epsilon, you act according to your policy that you've learned so far, like the argmax of your Q. Very simple, works really well, and we'll see a demo of it in action. But one issue with it is that there's really no way, again, like it doesn't tell us anything about this trade-off, because once you like eventually do explore the space, well, you would still be, if you have this very high epsilon, you would still be like motor babbling around, and you would not be doing as well as you could. So we would need to do something like manually, maybe start with high epsilon that does a lot of exploration, and then manually reduce it to have some lower epsilon that exploits. So essentially, we're kind of like hand controlling this exploration exploitation preference over time. And that's kind of like an annoying detail that people have to manually set, but I think people often do that. And we'll see a demo of epsilon greedy, but then we'll also see another solution, which is going to be exploration functions to address this trade-off automatically. So what we see now is this value of epsilon that you'll see in your project being controlled. And so when it's really, really high, we are doing, I should probably move the cursor around. We are doing a lot of exploration. So we're learning potentially a lot about the world, but as far as like actually moving forward, which is the goal of this crawler, we're not doing too well. So even if we go forward, oops. Even if we move forward quite a bit and we do a lot of learning steps, we still have this very, very high injection of noise into our control. So if we reduce this epsilon and now set it to 0.0, so there's no exploration, it's purely exploitation, we see that we can do well. So this was an example of controlling this exploration exploitation by hand. How can we control this automatically? Well, we can essentially keep track of where we've been and where we haven't been, and don't explore or don't move to the states, basically move towards the states that we haven't been many times in, but then if we've been in a particular state many times, we aren't as attracted or pulled towards it. And this can be formalized by using exploration functions, where, and again, you've seen something very similar with UCB1 heuristic in Monte Carlo tree search, where we basically have an exploration function f that combines the utility, or like the sum of all of the value, and the number of times we visited a particular state. And it adds them linearly. So you can think of it, really, if there was no exploration, we would just be using our values. But we have this little bonus, which this is a function that, as n increases, ends up decaying over time. So if we've seen n, if we visited n many, many times, this bonus is going to be very small. And we can look if the regular queue update that we've had before looked like this. Now we are going to modify it just by using this exploration function instead of the Q value. So this can be expanded to basically Q of S prime, A prime, plus 1 over K, the number of times that we've been in state S and had taken action A prime. And this works really nicely a lot of the time. And it, again, automatically, I guess the other bonus is that just as we were propagating rewards back, putting this bonus into our queue updates will propagate these exploration bonuses back as well. So if there is a state that we've reached once that we've said, oh, we haven't seen this before, it will propagate, and it got a bonus, will propagate this bonus back so that we are, even if we're far away from the state, we're more pulled towards it. So that basically pulls us towards attractive states. I'll do a little example of it, actually, in a different slide. So here is a visualization of such a count-based exploration policy and a epsilon greedy or random exploration policy. So I'm not sure I can control, I guess I can't control the playback here. But on the very far left in the video, you see this point in 2D. It's picking random actions. So it's kind of exploring, it's covering the space, and in mazes, it's also covering the space somewhat, but it still doesn't, it covers the space slowly. And so what we'd see in the middle and on the right is something that actually takes these counts into account. And so if the color is blue, then it means you've been to the state many times, so the n is high. And if the color is red, it means that state hasn't been visited, so n is low. And so you see kind of like this little heat map of visitation counts. And we're seeing that for the states that you haven't seen, we're very, very quickly covering them. And what you would see on the right as well is this type of bonus being added to queue updates, where you're intentionally planning to explore, or you're intentionally targeting to explore unseen actions and moving towards them. Whereas in the middle, you would see this bonus just being added greedily, where we're not like propagating these bonuses in our queue updates. Yeah, question? Sorry? The goal of this agent is 0 everywhere. There is no goal. The reward function is 0, so this behavior purely comes out from just purely the bonus, these exploration bonuses. Because you could see on the left, it's just aimlessly moving around. Good question. Sorry? The question is random exploration epsilon greedy? In this case, you can think of it, it's epsilon greedy with epsilon 1. So there's no policy. Just purely, this is kind of like the coverage that you would get if you were moving purely randomly. Which is still in two-dimensional space, it still does a decent job covering. It's just that as you get in higher and higher dimensional spaces, random walks are just really going to cover only a tiny fraction or tiny volume of the state space. And so these types of strategies might be a lot more important. Okay. So this brings us to another notion, this notion of regret that we've talked about. And again, it comes from this desire to try to somehow evaluate or benchmark the effectiveness of various exploration strategies. And towards this, we will write down regret as this measure, which is going to be the difference between your expected rewards that you've gotten as you were learning, and the rewards that you could have gotten. So the optimal rewards are like if you knew the MDP ahead of time and you did, say, offline planning, this would be the best you would be able to do. And so then you take the difference between the rewards that you've actually gotten by like making all the mistakes along the way while you were learning, and the best that you could have gotten. So it's not just measuring what's the behavior or what's the reward that we've gotten after we've done the learning, but also the path to get to that learning. We want to make that efficient. And this also comes up in not just in reinforcement learning, but in other areas of AI as well, and statistics. And yeah. Okay. Let's see, any questions about regret or exploration? Yes? Yeah, the question is, in this count-based exploration, is K here some arbitrary constant? And yes, unsatisfyingly, it is. It depends on typically the magnitudes of the rewards that you get in your environment. So you want something that can trade it off, because we don't know what the magnitudes of the rewards in the environment we get ahead of time. So we want K to match. And it would also, I would say, even then, we cannot think of it as like a percentage of those rewards, because some environments generally might require more initiative to explore, and some might require less. So it is a constant. But very good question. Any other questions? Yeah, the question is, in this modified Q update, what is n of S prime? And this is the number of times we have previously visited state S prime and taken action A. So just like a Q function, it's going to be a table of size number of states times number of actions. It would be like a two-dimensional array. And we would be, every time our agent visits a particular state, we would add like, increment this table by +1. Is that clear? Yes. Good question. Okay. I'll just check Zoom real quick. Oh, the question is, what is Polo? So Polo was one particular algorithm that we've introduced, targeting exploration and planning. I think the algorithm itself is not important. I think it was just, this was a useful visualization of counting. But it stands for plan offline, learn online, I think. Okay, so we've covered this, and our last topic of the day, we're going to talk about approximate reinforcement learning, but maybe this could be a good time to take a 3.5-minute break and resume at 6. All right, let's resume. We're going to cover now the last third set of topics for today, which is approximate reinforcement learning, dealing with large state spaces. And we're going to first look at approximate Q-learning. The goal that, or the problem that we're running into is that the basic Q-learning that we've seen just keeps a table of all of the Q values. So we assume we have some finite and countable number of states, some finite and countable number of actions. We build like a two-dimensional array of those, and that's our table of Q values. So it's just kind of like a lookup table. But there are two problems with doing this. One of the problems is that, well, we cannot possibly learn about every single state in the world during training. So we have to potentially make some more powerful inferences or generalizations and decide how to act without seeing certain states, but maybe transferring what we know from similar situations. So that's issue one. The second issue is that just this table, if we wanted to have this array, would be too large to hold in memory. So if you remember, like recalling back to lecture 2, when we were discussing state space sizes for even Pacman, well, if we just wanted to know where the Pacman is, the state space, the number of states might be somewhat manageable in the hundreds. But if we want to include other features in the state, like whether the dots are present or not, or the ghosts are and such, these numbers of states quickly grow astronomical. So we cannot typically fit all of this in memory. That's the second issue. We're just keeping tables. So towards this first one, this first issue, we want some notion of generalization. And for now, I will kind of hand wave my way through it. This notion of generalization we're going to make a lot more concrete, more formal in the third part of the course. But for now, I just want to give you some preview and how it relates to our conundrum here in reinforcement learning. Basically, want, as I've mentioned, to generalize to new but potentially similar situations. As an example, let's say we are in this state, and from this experience, we discover that this state is bad because maybe the next turn, the ghost eats the Pac-Man, so this is a bad state. But then, with naive tabular Q-learning, it doesn't actually tell us anything about this state. This state we still don't know anything about. But intuitively, you would think, well, we're close to the ghosts just as before. So probably, ideally, our agent should be able to generalize and decide, well, this is a bad state as well from having experience with this state. But that's not the case. Or an even sillier example, that we don't know that this state is also bad. Though it seems very, very similar, the only difference here is like one of the pellets is missing. But again, to naive tabular Q-learning, we also wouldn't know whether this is bad or not. So not a good situation, and we would like to address this. And the way we're going to address it is through tools that you've already used in adversarial search, which you've seen these things, evaluation functions, which describe some quantities at the time it was value, here it could be Q values, through some linear combination of features. And these features, they're something that returns a real number and typically describes something that we as designers of the methods deem to be important to the game. So now we're not necessarily writing totally generic algorithms. Now when we're using these feature representations, we're targeting the algorithms or we're targeting the solutions to a specific particular environment. So that's the drawback. Some features might be things like distance to the closest ghost from the for the Pac-Man, distance to the closest pellet, number of ghosts, maybe some other arithmetic expressions of these, and so on. So this is, you can go wild with this and come up with all sorts of things, try them and check if they're useful or not. And they can describe both the values of single states, but they can also be describing the values of states and actions, so Q values as well. Any questions or comments about this as a strategy? Does this strategy seem sensible as a way to deal with large state spaces? It's not perfect. It's not, personally to me, not super satisfying, but it's the best or one of the best things that we can do. So if we have these features, one of these, which we can call them here f1 to fn, we can then describe the value functions or the Q functions as linear combinations of these features. So if we're in a particular state here, instead of looking up the value, the Q value in some table, we're going to be answering or giving the Q value as some weighted combination of these features. And so these features are not going to be something we would just be able to read them off. But then how can we actually give or generate different Q functions? Well, we'd be able to control and tweak these weighting parameters W1 to Wn. So these are the only parameters of the Q function that we can control. Before, we could just, the number of parameters was number of states times number of actions. We basically set each state, we could change each state directly. But here we just have n parameters. So we've gone from this to this, which is now quite a cost saving. And it can be just summed up in a few powerful numbers. The issue or the challenge is that, well, you might have state aliasing, where basically the states, if we just express them, or these Q values, if we express them as this linear combination, well, for different states, you might actually get the same Q value. Or if we choose our features poorly, we might not be able to represent all the Q values with a poor choice of features. So for example, we only had one feature and it was like the size of the screen in the game. Well, no matter how we try to tweak this W, we wouldn't be able to express some desired Q numbers that we want. So choosing these features well is important. They need to be expressive enough. So now let's see how we could use these linear value functions to write or derive an approximate Q-learning algorithm. So we've said that we're expressing our Q values not as a table, but as this linear combination of features. We're starting with that definition. And then the question is, what does our Q-learning algorithm look like with these features? Well, just as before, from the environment, we get some particular transition. And as before, we looked, our difference, our temporal difference, is going to be this difference between the long-term value that we get based on the transition minus what our Q function tells you the long-term value is. And we saw that we would update this Q value by learning rate times this difference. So this is just the exact Q learning algorithm and update. This is what we've seen before. Now the question is, this operation, before it was easy because this was just a table. We just directly set, we wrote into one particular entry in the array. But we cannot do it now. The only parameters that we have to tweak are these W's. And the way that we can tweak them, and we'll get to the derivation and justification for why in a couple of slides, but for now I just want to share the result and the behavior and intuition for this result. The way we tweak our free parameters W is we increment them by the learning rate times this difference quantity that we've gotten times the value of the feature for this W. So again, this is somewhat unintuitive where it's coming from. We will describe, or we will discuss where, but for now, this is the update for the features. So now we have a way to say, okay, here's how the only parameters that we have to control, here's how they should be adjusted and controlled, as you see this little agent doing based on experience. And let's take a look maybe at an example of how this behaves. And I should say, these are, now this is approximate. So this is not exact Q learning because we might want to set a Q value to something, but we might not have the expressive power just by tweaking these W's to do it. So now our Q values are going to be approximate. Yes, question?
Why is the coefficient for Q is 1?
Sorry, the question is, why is the coefficient for Q1 instead of, because, so we've rewritten in the last lecture, this is a little switch that we've done to make notation easier. In the last lecture, we've written two different ways of writing this Q update. So we could have written it as 1 minus alpha plus Q plus alpha times this quantity. Or we could have, if we expanded it out, we could have just written it as Q plus alpha, this quantity, minus Q. Is this handwriting? Hopefully it's good enough to, okay, clarify. Yeah, good question. This is a little bit of a sneaky thing, I gotta admit, we've done to make this a little bit clearer. Any other questions? Okay, so what? Just let's maybe see some intuition for this. So for this example, so if something bad unexpectedly happens, what does this mean? Well, it means that we were expecting this Q value. So this is our previous prediction, what we expect to happen. We expected this Q value to be high, but then what we actually saw, which is this quantity that we got based on our incoming experience, it's actually low. So what this means is that this difference is going to be negative, or very negative. And it'll be then we will be plugging it in, and then the weight updates that we'll be doing, if we're assuming that the feature value is high, which is it's positive, we'll be multiplying a negative times a positive, and so we will be reducing the weight of this particular feature. So it says that we're basically like placing the blame on this feature if something bad happened. And we'll be reducing it, which would say, by reducing it, we would basically like drop, because the Q value is a linear combination of these features, by reducing one of the weights, we will also, as a consequence, reduce the Q values for this state. So that's kind of like how we would be reacting to these new events happening and adapting our Qs. And you can also like think through the example of if instead we expected something bad and something good happened, this difference would be positive, and you would see that we will actually upweigh, so assign credit to this particular feature instead. So that's the intuition for this update. And again, the formal justification, we'll see if we have time to briefly discuss it, is that we're actually doing online least squares updates to these linear functions. Quickly check Zoom for, okay, great. Questions getting answered. So let's take a look at an example, maybe for Pacman, where we have a Q function represented by these two features, which is the closeness to the ghost and the closeness to the dot. And we see that, well, we think closeness to the dot is great, closeness to the ghost is okay, but maybe not too bad, which doesn't seem like that would be very smart of the Pacman to think that. So we're in this state, and these are the values of the features in this state, and we take an action north. So our Pacman moves, our Pacman moves north, takes this action. So this is the expected Q value that we have in this function. So we think moving north is going to give us reward +2. Well, we actually do it. We find that we get eaten and we have some really high negative reward. So the action turned out to be unexpectedly bad. Then, so this was if we run our, or if we execute our count up, tally up, our actual long-term prediction. So then what happens? Well, we take the difference of actual and predicted, and we find out that it's highly negative. And we update the weights of these individual features. So the feature weight, it was 4 before. So we incremented by learning rate times the difference times the value that this feature has in the state. And similarly do that for the ghost. Before it was 1, incremented by learning rate times the difference times the previous value of this feature. And we arrive at an updated Q function that now says, well, being close to the ghost is basically downweighed. So being close to the ghost would give you negative, or give you, lower your Q values, or make them negative. So we've assigned blame basically to this feature and made it repellent. And as an example, here's just basically we can have from this very powerful update where we've got eaten only once, well, only twice. And we've quickly started assigning that being close to ghosts, just from 2 episodes of experience, we've updated this feature and said being close to ghosts is bad. And so now the agent our Pacman is acting in such a way that would be avoiding the ghosts from, again, from very little. Because the only thing that you're caring about here, and really are generalizing, is this closeness to the ghost feature. So, and that gets repeated, or this quantity gets reused in many states. It doesn't matter how many pallets are left. It doesn't matter where you are. It's just closeness to the ghost. So it's like, it's almost as if you're hand designing. It's like you're hand designing a bot, except now you didn't need to tune all of those weights and parameters by hand. They're automatically tuned by this approximate Q-learning algorithm. So maybe, let's see. Yeah, I think we still have time to go over it a little bit. Yes, question?
Do the initial values that you set for each of the WI have like an effect on what the W's eventually converge to?
Is the question, do the W's eventually converge? Is that the question?
I guess like, yeah, that, and then if they do converge, do the initial values have any effect on that?
And the question is, do the W's converge, and do the initial W's have any effect? And yes, so both, well, actually, sorry, I should say the W's in this case are not guaranteed to converge unless you lower the learning rate, unless you decay the learning rate. And does it matter where they start? In this case, I believe it does, because we're not guaranteed, because this is approximate Q-learning, so we're not guaranteed necessarily to reach the globally optimal policy. Again, if your choice of features is really bad, you're definitely not going to be optimal. And so that means there would be several kind of like local optima that you could fall into. And so the initial guess for the W's then makes a difference. Yeah. Great question. Any others? Okay. So this, I just want to say, this material, we want to briefly cover it as justification. Again, we'll talk more about it in part 3 of the course. And these parts are not going to be on tests or exams, because I think it might contain some material that you haven't seen before. But we just wanted to briefly go over it to not keep that update rule so mystical. So the way we arrived at it was via least squares, which is based on linear regression, based on linear regression, where we're trying to fit some linear functions, like a line, to a bunch of observations, like these red dots. And these linear functions, again, could be lines, could be planes, which have more parameters, or it could be hyperplanes in even higher dimensions, which would support more parameters. And the way that we would try to find those parameters W is by minimizing the residual between what we actually observe, which is our red dots, and what our linear function predicts, which would be the point on this line. And so we would be minimizing the discrepancy between them, or residual. And then the total residual is just going to be summed over all of these data points, or all the observations that we have. So this would be the sum over I. And we'd be looking at sum of squares of these residuals. And the reason we square them here is because it doesn't matter whether the difference is negative or positive between observation and prediction. We're just looking for the magnitude of the difference and trying to reduce that magnitude. And we also know, whoa, the PowerPoint is hanging and crashed. Oh, okay. We know that these predictions, they have this form. of some of our features. So the way we could minimize this error, this sum of all of these residuals, is we could use the tools of calculus, where this is a scalar, and we would be basically using or looking at the derivative of this error with respect to one of our parameters, or each of our parameters, w of m. And if you were actually to do this differentiation by hand, this would be the update, or this would be the derivative that you would get. And then if we wanted to minimize this error, we would be going in the direction of the negative derivative. Because if we went, basically this would say, if we nudge this up, then this error function goes up. If we nudge by this amount down, the error would go down. So we're doing, if like a negative here becomes a positive here. That's sometimes a point of confusion. And then we have a way to update our W's based on this learning rate, and that looks exactly like the Q update that we saw, where this value, this whole thing is what we called the difference, and this is basically our Q, like our target, and this quantity, this linear combination, is our form of the Q function that we've derived. There are some challenges to keep in mind with this, that we typically don't want overly expressive functions. We might want a line, or maybe something that fits it better, but we might not want a very high dimensional, high degree polynomial, because oftentimes it might do not sensible things outside of our data. So we want something that also behaves well outside of our exact data points. And this is a topic we'll talk about, again, a lot more in part 3 of the course. So we've talked about each of these topics. I think I might skip policy search because we've only have like a very, very brief coverage of it. Well, I guess, yeah, one thing I would say about policy search is that it's another additional approximate method where we aren't trying to tweak the Q function or the value function, because that seems very indirect. Like value functions just tell us how good states are. But we might want to just directly predict what would be the action to take. So we might want to directly tweak our policy function or optimize for our policy function. And we can tune it by hill climbing or local search methods that we've seen in I believe, last CSP lecture. We don't want to write out like exactly how it looks like, because I think there's a lot more subtleties to this. This is a common policy search, and policy gradient methods are another very common class of reinforcement learning algorithms. But I think to do it justice, it would need to go into this in a little bit more depth. But the intuition is that we are trying to do local search on these Q functions. So I think I would end it here and just say that we are done with part 1 of the course. And part 2 is going to be uncertainty and learning. And then part 3 is going to be more machine learning, neural networks, and optimization. So